Yes, ma'am. Yes, ma'am.
Brian, I need one small help. Can
Yeah.
you log into the poster webinar link also? And
Okay.
if anyone is coming, just give me YouTube live stream so that we can join.
I'll do that, ma'am.
Okay, thank you.
Okay.
Brian couldn't perfect.
There's an echo, man.
Brian, we are going to play this song. Just see whether it is audible or not.
Okay. Sound is not audible now, and there's an echo that is coming.
Now,
Echo is still there. From your mic. Yes. I'm on headphones. I don't know. Now I'm not able to hear that feedback.
good afternoon, everyone. Good afternoon, Brian sir.
Good afternoon.
Sangeeta, now that echo is starting
Yes.
when you just spoke.
Yeah, I could also hear some echo.
Asil, are you there? Asil? I have sent you a mail. Can you just check the prayer song?
You just try presenting also. And Brian sir, please note whether the echo is there.
Okay.
While I am talking, is it fine, Brian sir?
There's no echo now, ma'am.
Okay, fine.
It's fine, Gayatri ma'am. No echo now.
Okay, Mandira ma'am.
Yeah, we could hear an echo now.
Now, ma'am.
Yeah, ma'am, some noise is there.
And there's a distortion, but when your mic is on, we can hear an echo.
Now is it audible, Brian sir? Is there an echo?
No, ma'am, it's fine.
Okay. Hi, KK.
Hello Gayatri, how are you?
Fine, how are you?
I'm good, I'm good.
All
Thanks for
prepared?
inviting me anyway.
It's our pleasure. It's our pleasure.
Yeah.
Okay, so in this link, we have our faculty. Sangeeta George ma'am is HOD. Mandira ma'am is from chemistry department. Brian sir is from physics department.
Hello everyone.
Hello,
Hello,
sir.
Okay, and Sherin is from chemistry department. And Asil is our technical support.
Okay. Nice to meet you all anyway. It's actually good morning here. It's 8:30 around here. Probably good afternoon there.
Yes.
Anyways,
So better you can say good afternoon since we have
Yeah.
afternoon here.
yeah. Can for the time being, can we check something actually quickly? We usually don't use. I usually don't use Google Meet. We have Teams more popular here. So I just want to quickly check if you can see the
Yes, no
slides.
problem. Yeah, no problem. You can just check your presentation, all those things.
Please go ahead.
So can you see this now?
Huh?
Can you see the
No, sir.
screen? No.
No, you have to present now. You have to
Yeah.
click the present now, then
Yeah,
only it
yeah,
will
yeah.
come.
No. Can you
Yeah,
see
yeah.
this? Yeah. Okay.
Yes,
yeah.
coming.
Okay, that's cool. Okay, great.
Yeah,
Yes,
done.
sir.
Yeah, thanks.
Light of the world, you step down into darkness. Open my eyes.
Asil, it's not audible. Asil, can you hear me?
This heart adore you. Hope of a life spent with you. King of all days, so highly exalted, glorious in heaven above. Humbly you came to the
Yes.
earth you
Now it's coming.
created. All
Yeah.
for love's sake became poor. Here I am to worship, here I am to bow down, here I am to say that.
Hello, VK.
Yeah, I can hear you.
So good afternoon to you. We have few of our department members here.
Okay.
Gayatri ma'am had contacted you regarding the webinar. So she is from the physics department. We have Mandira ma'am and Sharon ma'am from the chemistry department. Also with the Gayatri ma'am is our HOD, Sangeeta ma'am.
Okay.
Hi, VK.
Hello.
Very happy that you could make it.
Yeah, no problem.
Hello, Manu. How are you?
Hello, I am good. How are you?
Good, good. Good morning.
Hi, Dr. Manu C.
Hi, hi.
How are you?
Good, good. How are you?
Good, 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 good. Thank you. Good afternoon, Father.
Yes, very good afternoon.
Good afternoon, Father.
Yeah, good afternoon.
Good afternoon, Father.
Good afternoon.
Anna, we can start the program.
Yes, ma'am.
Okay.
Good afternoon to one and all present here. Socrates once said, and I quote, "The only true wisdom is in knowing you know nothing." Hence, gaining knowledge is a step by step process, starting from the point when you realize that whatever you knew was nothing. So, I welcome you all to the international webinar on applications of optical instrumentation, ultrafast spectroscopy, and spintronics. Prayer is man's greatest power. So let's start the day by invoking the blessings of the Almighty. I request Azil sir to play the video.
Light of the world, you step down into darkness. Open my eyes, let me see beauty that makes this heart adore you. Hope of a life spent with you. King of all days, so highly exalted, glorious in heaven above. Humbly you came to the earth you created, all for love's sake became poor. Here I am to worship, here I am to bow down, here I am to say that you're my Lord. You're altogether lovely, altogether worthy, altogether wonderful to me. I'll never know how much it costs to see my sin upon the cross. I'll never know how much it costs to see my sin upon the cross. Thank you.
I request Dr. Sangeeta George, Head, Department of Science, to welcome the gathering.
Isaac Newton said, and I quote, "What we know is a drop, what we don't know is an ocean." And I unquote. Reverend Dr. Father Babu Paul CMI, Principal, Christ Academy Institute for Advanced Studies, distinguished invited speakers, Ms. Gayatri Mohan KV, co-convener of this webinar, faculty members from Department of Science, participants, and my dear students. A warm good afternoon to one and all present here. It is both an honor and privilege to stand before you today and to welcome you to the international webinar on applications of optical instrumentation, ultrafast spectroscopy, and Spintronics. We are honored by the presence of Reverend Father Dr. Babu Paul CMI, Principal, Christ Academy Institute for Advanced Studies. Father have a teaching experience of more than 22 years. Feathers on his cap include Research Guide under Calicut University, Reviewer of International Academic Forum Japan and Salamanca University, Spain, peer team member of National Assessment and Accreditation Council, NAC, and the list goes on. On behalf of all gathered here, I welcome you, dear Father. We are indeed delighted to have with us our esteemed guest, Dr. Krishnakumar Chullapillai, Dr. Manu Chenchalian, and Mr. Venkata Krishna Bharadwaj, who will enrich us with their expert knowledge and insight. On behalf of all assembled here, I welcome you, sirs. Cordial welcome to Ms. Gayatri Mohan KV, co-convener of this webinar, and all the faculty members from Department of Science, CAIAS. Albert Einstein once said, and I quote, "I have no special talents, I am just passionately curious," and I unquote. I would like to welcome all the participants who are part of this webinar due to your mutual passion for the subject. We are very delighted and honored to have received more than 300 registrations, and I'm grateful to all of you for accepting our invitation. I hope this webinar will be a perfect platform to stimulate, build, and strengthen your intellectual mind. Last but not the least, on behalf of the organizing committee, I extend a warm welcome to each and everyone. Thank you.
Thank you, ma'am. I now request Professor Gayatri Mohan KV, co-convener of this webinar, to brief about the webinar.
Thank you, Anna. Good afternoon, everyone. I would like to draw your attention here and wisdom in the hearts of all, thereby enlightening the various strata of society, irrespective of gender, caste, religion, and region. Christ Academy Institute for Advanced Studies is dedicated to Jesus Christ, the Supreme Guru, who is guiding light to enlighten every individual who is a part of our academic community. Our source of inspiration is the founder of CMI, Saint Kyriakos Elias Chavra, a great educationist who brought about revolutionary changes in the society through his decisive mission and far-sighted vision. CAIAS was established in the year 2016 and is affiliated to Bangalore University. Spread in 33 acres, CAIAS offers 10 undergraduate programs and 5 postgraduate programs. Department of Science is one of the major departments in the college, which helps to create scientifically literate and technologically capable problem solvers to comprehend global issues. We, at the Department of Science, nurtures a learning environment for high-quality education by providing scientific depth and state-of-art facilities. The department offers 5 BSc programs: BSc Computer Science, Mathematics and Statistics, BSc Economics, Mathematics and Statistics, BSc Physics, Chemistry and Mathematics, BSc Physics, Computer Science and Mathematics, BSc Journalism, Psychology and Computer Science. Department of Science have experience in academically oriented faculty who are actively engaged in the research areas of fluid mechanics, fuzzy theory, optics, hydrometallurgy, astrophysics and electrochemistry. In many respects, research findings are only as valuable as how well they can be put into practice to improve outcomes. Whatever be the outcome, we often require guidance from the vast literature as to how to put rather complex findings into practice. In this webinar, our distinguished speakers will discuss many aspects of 3 different research fields. The presentation includes practical applications of optical instrumentation, ultrafast spectroscopy, and spintronics. Hope this webinar helps you to gain information in your field of study. Thank you.
Thank you, ma'am. I now request Reverend Father Dr. Babu Paul, Principal of CAIAS, to address the gathering.
So very good afternoon to everybody. I hope you can hear me, okay?
Yes, Father.
Yes, okay, thank you, yeah. Dr. Sangeeta George, Department Head, Ms. Gayatri Mohan, the coordinator of the program, eminent invited guests, the panel of resource persons, research scholars, students, faculty members, and my dear friends. I'm so happy to be a part of this international webinar on optical instrumentation, ultrafast spectroscopy, and Spintronics. And it's rather a good time for all of us to come together on this online platform. Today, nowadays, we know that generation of knowledge and organization of knowledge has become so mandatory for any higher educational institution for that matter. And added to that, the with the advancement of science and technology, it has become a compelling priority for any educational institution in order to make their presence felt there in the academia. And during this pandemic time, it's rather a good initiative there from the part of the science department, the Christ Academy Institute for Advanced Study. As such, they have taken the initiative in order to reach out to other academic communities so that they would be able to share their academic expertise on various levels. How far we would be able to make ourselves so meaningful depends upon the type of involvement what we have. Today, it has become so mandatory for all educational institutions and research scholars who are involved there in research and teaching and learning process to come up with the new advancement there in one's own field. Updation by way of sharing the knowledge and experiences, and as such gives us a rather good insight for the scientific community so that they would be able to come together and have a rather good discussions on those topics, and will have something to take away as a part of this participation in this international webinar. Today, we are really happy to have you as a part of this online platform. And it has been added pleasure for inviting you so that we also would be able to share ourselves there with the rest of the academic communities. And also, for this one should be understood as a kind of addition, a kind of updation of the knowledge there from the faculty point of view. Students and people who are involved in research and the research scholars definitely is looking forward this as a platform in order to update themselves in their academic journey. Today, as we gather together here on this online platform, let's be aware of the challenges there in front of us, especially during this pandemic time, a rather hard and tough time. What all things or whichever be the means, we would be able to reach out there to the academic community, there to the researchers, there to the students and faculty members has become inevitable. Today, let's try our level best so that we'll be able to have something solid for the rest of the academic generations ahead. I appreciate and extend my gratitude to Dr. Sangeeta George, the head of the Department of Science, and also Ms. Gayatri Mohan, who has been coordinating the events, and also all the people who have, the faculty members and the student community who have put in effort in order to put up this program during this pandemic time. I wish you all the best, and also I extend my support and in such a way so that we would be, the scientific community would be able to get back to us, and we will be able to come up with certain programs of this kind as a part of our academic updation and also sharing our expertise. Congratulations to all the people who have been behind this, and also I wish all the best there for all the participants of this online platform. I wish you all the best. May God bless you. Thank you.
Thank you, Father, for your inspirational words. I invite Dr. Brian Ritesh Miranda, Assistant Professor, Department of Science, to introduce the first speaker, Dr. Krishna Kumar Chullipandavil.
Thank you, Anna. It is my great pleasure to invite Dr. Krishna Kumar Chullipandavil to this event. To say a few words about him, he has completed his Masters of Science and Technology, MSc Tech, in Photonics from the National Institute of Technology, Calicut. He completed his PhD in Physics in Fluorescence Spectroscopy and Optical Instrumentation from the University College Cork, NUI, and is pursuing his postdoctoral research at the Center of Advanced Photonics and Process Analysis, CAPA, Munster Technology University, Cork. His major role being management and technical supervision of pharmaceutical industry associated projects. He has his expertise in optics and spectroscopy, including the setup, development, and alignment skills, optical instrumentation, hyperspectral imaging, optical manipulation, high power laser applications, 3D designing and printing, to name a few. His recent publications in the last year, that is in the year 2020, are titled as follows: Deep UV laser induced fluorescence for pharmaceutical cleaning validation in the Journal of Analytical Chemistry. COVID 19 mask efficiency is dependent on both fabric and fit, published in Future Microbiology. Recent improvements in deep ultraviolet fluorescence devices for cleaning verification, published in the European Pharma Journal. UV excited fluorescence spectroscopy for the determination of reconstitution time of an in vial lyophilized product in the International Journal of Pharmaceutics, to name a few. Among his achievements, the foremost is that he has been a third rank holder in the MSc Tech Photonics National Institute of Technology, Calicut, and recently in the year 2020 has been awarded the Best National Research Image of the Year award by the Science Foundation of Ireland and Innovation Partnership Program grant for the association with pharma industry. I welcome you, sir, to this event. Sir, you're on mute.
Sorry about that. So yeah, thank you for the very nice introduction there. I'll straight away go to the presentation. So yes, I hope you can see my slides there.
Yes, sir, it is visible.
Okay. So I've been researching in Ireland for like almost 10 years now, and my field is majorly optical instrumentation for industries. So before I go through the main topics that I've been working on the last year, what I would like to introduce to you is like, the background where I'm from, like, and also what I work on. So I work in this university in Ireland called Munster Technological University. It is a multi-campus technological university with 6 campuses across Ireland. So our campus is located in the southwest region of Ireland. There are 2 main institutes which primarily comprise the university. One is the Cork Institute of Technology, where I belong, and then there is the Institute of Technology in Tralee. So these Institute of Technologies are similar to the Indian Institute of Technologies, or IITs, that we have. The particular group that I'm working on is called CAPA, Center for Advanced Photonics and Process Analysis. It is a technological gateway. There are 15 technological gateways in Ireland, sorry. So they form a bridge between the industry and academia. So what they do is like they share technologies to the industry. So researchers would work very closely with industries. They would deliver technology solutions to the industry. So the industry would approach you with a problem that they are currently facing, and then you would suggest a solution, or would rather give a full size product for them. So at present, we are around 33 people working as a group. We have been awarded over 10 million euros for the past 5 years. We have currently over 20 projects working over 100K euros, and we are engaged with more than 100 companies over Ireland and over abroad Ireland. Over 90 publications over the last 5 years, and we have been collaborating with 11 of the top 100 universities worldwide. What we do as a group is, as I told before, we provide a bridge between academia and the industry. So for that, we use photonics. So photonics is basically the science of working with light. We provide light-based solutions to whatever problems the industry face. Like, for example, in communications, we provide solutions for powering fast internet and data centers. In energy harvesting, we have a big group in Tyndall National Institute working in photovoltaic solar cells. In manufacturing, we help them optimize process monitoring. For transport, there is being research carried on enabling self-driving cars. In the field of health, we are working in the field of medical imaging, in environment, advanced sensors, and diagnostics. So we are capable of this using these major techniques, imaging and microscopy. The microscopy include both, electron microscopy and also optical microscopy. Then spectroscopy, all kind of spectroscopy, fluorescence, Raman, near IR, most of them. That is the field that I am mostly working on. Sensing and detection for environmental monitoring or water and soil analysis. Process monitoring, inline, online sensing. Nanophotonics, we have works carried on photonic crystals and hybrid lasers and all of this stuff. So these all are kind of, the broad scenario. I'll come into much narrower version, which I'll be working on. So what I do predominantly is I work in the field of optical instrumentation. So I coordinate and supervise projects, regarding building optical instruments or, building ideas for instruments such as, say, for example, sensors. Say, if a company approaches you, or even you get a new idea for a gas sensor, you submit a proposal to a particular funding agency to using that idea, and then you either get a grant or you work for that company for developing that technique. So basically, optical instrumentation is a branch of technology in which more or less sophisticated instruments are constructed that make use of the optical phenomena. The techniques that I use primarily include fluorescence, Raman scattering, and imaging-based instrumentations. The main industries that I've been liaised with is pharma, biopharma, and food industry. These are the three main industries that are very strong in Ireland. The application areas that I've been working on include verification of cleaning in industry, product quality control, and product process control. So that is the gist of what I kind of do in here. And so for the next 30 odd minutes, what I would discuss it would be like two solutions that we provided to the industry. There are more, but with the time restrictions that we have, we can't provide more than two. So basically, I'll be going through two techniques that we used to solve two major problems in the industry. So the first association that I had when I joined the group, or when I moved to the current group that I'm working in, was with the pharmaceutical industry. So that was in the field of cleaning validation. I don't know how many of you have actually background in the pharma cleaning process and everything, but I'll try to explain it to you step by step. So the problem, the story behind the problem is that there is a funding agency in Ireland called PMTC, Advanced Technology Solutions in Pharmaceutical Manufacturing. So it's an association of the pharma companies in Ireland. So pharma companies in Ireland do include GSK, Lilly, Pfizer, Abbott, Merck, etc. So if you haven't heard of GSK, to just give you a context, GSK is the manufacturer of products like Horlicks, and all those products that you see in the screen. So these companies are strong worldwide, both in Ireland and around the world. So we were invited to have a site visit to check the problem that they have, and we got to go to Pfizer, Lilly, and GSK and check their their cleaning validation procedures and everything. So the problem that they had was that they had a loss of production time due to a cleaning verification delay. So I'll tell you what the delay is. So basically, each time they make something, they had to spend a lot of time for cleaning, so that they lose that much time to make another product. So, and this loss of time that we are speaking in is actually in terms of months. So it would, like if you take a year, they lose 2 or 3 months basically by cleaning. And I'll tell you why. So I'll take you through the cleaning cycle in the pharma industry. So if you ever see tablets or any other products, pharma products or even biopharma products, basically how they make it is that they have these huge vessels and equipments in their plants. And before before a tablet reaching acquiring this primarily form, they will be kind of like powders. Yeah, so they'll have a one main component in it called an active ingredient, and then there is additional sugars or something. Like for example, in paracetamol, you have the paracetamol, which is the chemical, and then you have the additional sugars in it. So each time they make it, they have to make sure that everything is clean, everything is extra clean. And when I say clean, I'm talking about like it's not visible clean. So visually it can be clean, yeah, of course, but it has to go par that so that not even parts per billion of their previous product should be appearing in the next batch of their production. So at the end of each batch, they have to make sure that this environment is extremely clean, so that they don't contaminate their future product. And when you're taking cases of like cancer drugs, and this can be extremely lethal, you can't do an overdose in the next batch. So this cleaning process becomes extremely critical. So usually what they do, this is actually from a real plant. So what they usually do is that they have these huge vessels in which they cook up this whole medicine. So they make the whole medicine and clean the whole equipment using water flow systems and stuff like that. And then there would be one cleaning personnel. There would be an engineer associated with that. It's called a cleaning validation engineer. So he or she would be getting, someone has to get inside the vessel, and then they have to take a sample. They would dip a cotton swab in ethanol or some other solvent, and then they would scratch it across the wall, and then they would take that swab into a solvent of ethanol, and then they would take to the lab for analysis. So this whole process is basically like you have to run a cleaning cycle, then measure a swab, and then take the lab for analysis. If the lab provides enough data to show that your environment is not clean, you have to run through that whole cleaning cycle again. So most of the cleaning cycle as a result of this runs from hours to days, mainly because your lab actually spends like 5 to 6 hours. They usually use techniques called liquid chromatography that they use for this. So the whole delay causes because you have to take the sample to the lab. So and they lose loads of days, and then they lose a significant amount of revenue for this. So for the basic problems that they kind of face is that one is the time delay, that you have to take the sample to the lab, which would take 5 to 6 hours for one particular cleaning cycle. And the solution that then we have is that if you can measure it on site, like if you have an instrument that can measure or check the cleaning at the particular site itself, then you don't have to take it to the lab and then do all the whole process. So at present, at that time, what they used was like a UV torch. So basically, this is similar to a normal UV lamp. If you shine it to any surface, any stains would appear as it is. The problem with this is that there is no, you don't get any any quantitative measurement out of it. You don't know how much amount is left over there to ensure that it is particularly clean or not. Another problem is that the personnel has to get inside the vessel. So there is no reachability in so-called called as hard to reach areas. So a solution for that is either that you have a torch like this, or you use a probe like this. So if you have a long wire running in through, you don't need to reach in there. So when PMTC or the Pharma Association approached us with this particular technique, we thought of using fluorescence for identifying a particular product. So fluorescence is a phenomena when you shine light upon something. Say you use yellow light to generate fluorescence, just like an incandescent lamp that you have in your home. You get something like a green, something like a red out of it. So basically what is happening is that light energy is converted into light energy itself, but that there is a loss of energy in between. So you don't end up with the initial frequency or particular wavelength of light that you use. So we proposed the technique of deep UV laser induced fluorescence. So deep UV is the wavelength that is shorter to the visible wavelength, that is way shorter to the visible wavelength, so that you don't get any interference with the normal lamps that they use back in the plant. So just to go through some physics, basically what happens is that you shine some laser light, you have a molecule or an atom that is in the ground state, and you excite it to an excited state, and you have some vibrational relaxation, and from the lowest vibrational state of your excited state, your atom or molecule relaxes to the ground state, and this whole process ends up in releasing photons or light, basically in a different wavelength, which is longer to the original wavelength that you used for excitation. You can record this light and generate what is called a fluorescence spectrum. So fluorescence spectrum is basically when you measure the intensities across the particular emission wavelengths that you get. So the whole idea is that we would use UV laser light to excite the particular trace molecules that is present after cleaning, and the fluorescence is generated by the particular active ingredient which can be captured by the detector. So the solution that we propose would have advantages by its own. The good thing is that the whole process of sampling and then dedicated lab space requirement is not needed anymore. You can just have one production cycle, and then you can take your instrument onto the site, and then you can shine your laser upon, detect the fluorescence, and then decide whether to start or stop a new cleaning cycle. We made a prototype for an initial stage, which can only be used in a lab, so that we can show the industry that we have this particular technique that is actually working in the lab. Then we can further develop it into the as an on-site instrument. So this is our instrument. So the cylinder that you see is actually a laser cavity. You would have laser light coming out of it. It would bounce off back from a couple of mirrors, and then it would be taken out to a fiber. And the fiber end, which I'll be showing you in the next slide as well, would be given into a collimator, which would focus light onto a particular metal sheet. So the metal sheet that we choose is kind of it's actually exactly the same thing that they use in the industry. So we would stain the metal sheet and then shine laser light on it, and we record fluorescence out of it. That's the general gist of it. That's again the particular setup. So we use two kinds of spectrometers, but basically detection instruments to record the fluorescence. This is what it looks in the end. So you have a long fiber coming out of it, and you can see that basically UV light is not visible. Yeah, you wouldn't see light as it is, like if you use a red or a green laser. So you can only see the fluorescence generated. Like in this case, you have a paper there, so you can see the laser light. You can see the fluorescence coming out of the paper once the laser is actually upon it. So up to going through more boring details of it. So the thing is that we kind of conducted experiments with different samples, with different medicines, basically, that we got from industry. And the good thing is that the instrument could distinguish between all the samples that they gave. And also it could distinguish between all the particular cleaning solvents that they gave as well. Another great factor was that the fluorescence generator, or the signals particularly generated by the instrument, was not interfered by what kind of particular material that it was on. Like, it can be a steel vessel, it can be a polymer, like for example PTFE, or even plastic pipe. So you can point the fiber or the probe head into the steel pipe, and then you can take measurements based on that. It would work on glass, so they have vessels made out of glass as well. So it worked on pretty much everything, and which was actually good for us. So the idea got well accepted, and then we kind of published it in a reasonably good journal. And the good part is that we show that to the companies, and then we got new opportunity for funding as well. So we are in this current year, we are now starting a project to improvise the instrument that I had showed you before. The basic idea would be to miniaturize it further, and also to give more features to it. Like, for example, at present we can only say measure fluorescence or measure a particular signal from it. The next idea is to have an imaging system to it, so that we can actually capture photographs of a particular stain, which is normally not visible to the human eye, while it is visible to the UV fluorescence spectrometer. So you would capture a particular area, and you can pinpoint out, and you can document it later, which is really helpful for the cleaning validation engineers, so that they can document the whole process. So that is one application that we kind of developed into a great idea. And since this is COVID times and we all have to wear masks outside, I think this next topic would be an interesting and relevant one. So the next application is basically for quality control of masks. So we used imaging techniques to check mask efficacy. So by mask efficacy, I would mean how much how safe you are by wearing a particular kind of mask. So that depends on how much transmission of breath that you have through the mask, sorry, and also that's how much leak the mask produces. So you might have noticed already that while you wear masks and then you have goggles over it, you cloud your goggles quite often, and then you find it really hard for finding a visibility really hard. So that is because your masks have leaks on the sides and also from the sides of the chin. So how we reached upon to this is that there is a European Committee for Standardization of these particular, clothing materials or any kind of materials that they use for health purposes, like, for example, PPE kits and everything. So what they noticed is that upon the rise of COVID, so many companies started making of these masks, like using cloth and other fabrics. The problem with them was that they were of cheap quality. So they came on to one of my colleagues, Dr. Stephen Darby. He's actually a member of the European Committee for Standardization. And they were like, masks with poor quality are getting really popular. And then, some form of protocols have to be established for these companies to manufacture a mask. So if they have this set of protocols or guidelines without which they can't make the masks, all the masks would be kind of standard. Like, at least they would be, trustable. So the task upon us was like to measure mask performance, which can simultaneously assess both fabric penetration and leakage due to poor fit. So poor fit basically means if a mask is loose or if it doesn't fit a particular face or body size, then that becomes a problem again. So in order to facilitate that, we had to make a setup which would assess or check leaks and transmission of the masks that we use normally. So the solution that we immediately posed was that, why can't we take the pictures of the leak of the breath that we have upon wearing a particular kind of mask. I mean, that's a seemingly very easy thing to do, because all you have to do is take a picture. But the problem is that you don't have, with normal eyes, you can't do that. The solution then there you can do is that you eliminate that leak. You eliminate the particles coming out of it using a very bright source. So what we suggested to the standards committee immediately was that we use extremely bright light sources to eliminate the aerosol particles coming out of mouth. So aerosol particles are like particles of few micrometers and less that can be of liquid or gaseous nature. So they are suspensions that you can even imagine water vapor molecules that are floating through air that can be treated as aerosols. So we had to make sure that whatever particles that is coming out of, say, a breath, that has to be coming in line of a very bright light source. So we used a normal red laser. We converted that normal laser beam into a laser line. So for that we use there are particular optical components called laser line generators, so that if you shine that laser into a screen or a wall, what you would see is like a line. Similarly, there are laser cone generators, or like laser circle generators. So basically what you do is like you pass your laser beam through a particular kind of lens called axicon, and what you would end up is like a circle. If you shine the light onto a wall, what you would see is like a circle. So you would place these two lasers across the face, like in like the sheet would come up across your face, and the cone would curve across your face as well. So for initial experiment trials, we were never going to experiment on a human, definitely. So we had to get a mannequin for that. So we have we got an experimental mannequin which is used for medical studies, which has an artificial lungs, and which they actually used to teach medical students back in the university here. We simulated breath conditions that normally have. So it's like a half a liter per breath that you have to give. So you would fill up the artificial lungs using a nebulizer, using a solvent. We used sodium chloride, like salt solution, for initial experiments. And then you press the lungs so that there will be a puff coming out of it. And then we kind of automated it using a mechanical instrument, so that the mechanical instrument will squeeze the lungs, and then a breath will be produced each time. So next target was to get the laser in line of it. So this is basically the laser cone that we used. We used a blue laser. It's not really blue, it's kind of cyan. The particular wavelength that we used is 488 nanometers. So you use your laser, you focus your laser around the sheet, around your face, just like that. And then you have a fume extractor to take out the breath, take out whatever breath that is coming out of it. We placed a high-speed camera across it, and we recorded images basically with that. We also used another laser along with it, which is a red laser sheet. So you would have a laser cone coming out of it and a red laser line like that. So that is basically how it would look like. You can see that there is one breath coming out of it, and then these are at extremely dark conditions, and we got this using a very good camera, reasonably good camera actually. So what you see is actually, you wouldn't see immediately, but you image it and you see actually. So you would, with imaging, we used like over 30 frames of a breath. So you would have a breath coming out of it, a plume would develop, and then it would die off. So we measured the breath for like different masks that we use. We used a medical mask and a FFP1 mask, and to check if this particular setup can be used for checking these particular masks. So the curved sheet kind of got leakages around. So this is something that we didn't expect, that leakages can originate from places like that, like where you have a gap between your chin and the ear, and you have a huge penetration with bandanas. So bandanas are like just face coverings, cloth face coverings. So they show how bad they are actually. Like, most of the people doesn't know this, and then they use a just a cloth to cover their face, which is not really safe. So we are in sort of the next step is actually to quantify this, how much transmission is there, and by calculating the particular brightness in each image. So we got like very fine set of color images by combining the results that we got. So this is a person wearing a mask, and then obviously when you don't wear a mask, this image got really popular, and I'll tell you why later. This is again 3 different masks type, and then you can see that the person who's not wearing a mask properly, like again, that's a tendency that most people do, that when you don't cover your nose as well along with the mouth, which again provides like lot of leaking, and when you wear it properly, there is only leak through the sides, and that goes upwards as well, which is not really, you don't give a transmission to the next person standing. This is again, this is a normal cloth mask that you use. You can see the higher amount of transmission there. This is a mask with a filter in it, and this is the normal medical mask essentially, and you can clearly see the differences in both. So the red that you see is using the red laser, the leak detected using the red laser. The blue or the cyan that you see is the other laser that is detecting the leak. We got extreme traction, we got extreme popularity for this particular image, because that won the research image of the year in Ireland in the year 2020, and most of the the newspapers and the news covered this, and it was mainly because it was extremely relevant at that sense, and people were reluctant to wear masks. There was protests coming out of the fact that they were forced to wear masks and everything. So since that, we totally enjoyed the popularity, and then the university was so kind to us. So that's me and my colleague who developed the tech, and then since the image won the Research Image Year of the Award, we have that billboards everywhere in the university for the students, for making sure that the students are aware of the dangers of it. Again, if you need further details regarding this, this is a published work, and then you can find the published work online. So that is basically what I've been doing for the past year or so. There are like plenty of other techniques that is being used parallelly. Like, for example, we do works on Raman scattering for find out, like, for example, if you have a tablet, how much % of the tablet is actually the original chemical that you use for the patient, and then stuff like that. And to conclude, basically what I've been discussing with you is optical instrumentation in industry. Optical instrumentation deals with building instruments based on using light as the primary tool. And I've been discussing with you a couple of applications in the pharma industry, and also in the quality validation for mask efficacy. So in pharma industry, the particular application that we use is cleaning validation, which is a very prominent problem that they face. And we use deep UV laser-induced fluorescence spectroscopy for that. And for the quality validation or the mask efficacy, we used a laser cone and laser line for imaging using a high-speed camera to analyze, how much leak or how much transmission that a mask can provide. And the industry, a particular company that is making a mask, can do quality control using this particular setup. So I thank everyone for patiently listening. Now if you have any questions, you can straight away shoot up.
Participants having doubts regarding the topics discussed can post their questions in the chat box available in the YouTube chat.
So just a question regarding the masks.
Yes, yeah.
Which mask would it actually be useful in wearing on a day-to-day basis? Because the amount of mask usage for a person on a day-to-day, weekly, we would need minimum of 7 masks. So like that, depending on the cost as well as the type of mask, which would be a very good one to wear, not only to stop bacteria and dust, but also these small viruses that do come in, common cold and flu.
Yeah, so not basically you can't make sure that you are 100% like safe. Even if you wear a surgical mask, there is still a transmission through. So from our studies, what we found out that if you have a 2-layer cotton, that is the cheapest solution that you can have, like a 2-layer cotton. So you have your thread like that, and then you have the other thread like that. So sorry, yeah. So you have a couple of you have, say, your couple of threads like that. Then that would provide reasonable enough security. The next option is that you have 2 layers and then you put a filter inside. So you might have seen cloth masks with filters. So these filters make sure that the particles around more than, like, say 5 micrometers are not entering your particular your mouth or the nose region. Then definitely the most safe and safest way is the surgical mask, but then cost becomes a factor as well, as you said. So yeah, those are the 3 options that you can use, but anything is better than not wearing them. So
Yes, sir. Thank you. So another question from me.
yeah, sure.
You've been working on UV fluorescence devices for cleaning verification.
Yes, yeah.
So these are mostly pharmaceutical devices.
Yeah, they are intended mostly for pharmacy, but they are general devices. They can generate fluorescence out of any particular sample.
Okay, thank you.
So is there any other? So do you have any questions? Anything other than that from the? Anyway, if you have further questions, you can always contact. Gayatri should have my contact anyway. So
Thank you, sir. I now request Dr. Rosebindu Joseph, Associate Professor, Department of Science, to render the vote of thanks.
A very good evening, everyone. It's my great privilege to propose a vote of thanks to our first speaker, Dr. Krishna Kumar Chullipalli. The research works and your findings that you shared with us today are really interesting and very informative, especially the mask efficacy by imaging. Your enthusiasm in your research field is contagious, and we are grateful for the time and effort you took to share your thoughts and experiences with us. Our institution would like to associate with you again, and we hope to hear from you more in the future, sir. Thank you. Thanks a lot, sir.
thank you very much. It has been a personal privilege for myself as well, and I thank all the committee and all those who are hearing for spending your time. And it's always a pleasure to share knowledge and information to everyone. So And thanks, Gayatri, for inviting me, and everyone again for patiently hearing it. Thanks. Good luck, everyone.
Thank you, sir. Thank you, ma'am. I now request Ms. Sharon Ryson, Assistant Professor, Department of Science, to introduce the second speaker, Dr. Manup Chinchilian.
Good evening, everyone. So I'm so honored to introduce you all the second speaker of our event, Mr. Manup Chinchilian. He is currently the Werner Grant Postdoctoral Fellow and doing his research in the area of development of femtosecond time resolved infrared absorption spectroscopy setup for the studies of photoswitchable proteins. And he is doing his work in the University of Gothenburg. And he was also the Israel Higher Education Council's Outstanding Postdoctoral Fellow for the year 2017-2019. And he has also worked as the laboratory specialist in the Laboratory of Biophysics in the Institute of Physics from the University of Tartu in Estonia. He completed his doctoral studies from the University of Tartu, Estonia, and the Master of Science and Technology in Photonics from NIT Calicut. He has got a large number of publications in different international and national journals, as well as his works were presented in many reputed conferences. So without any delay, I would like to hand over the session to the speaker, Mr. Manup Chinchilian. Over to you, sir.
Hello.
Yes, sir, you're audible.
Just give me a second. I am trying to connect from my laptop. I don't know where is the link. So I was in my phone. Gmail. Where is it? Gmail. Yes. Hello. Hello. Okay, I should delete from here. Hello.
Yes, sir, you're audible.
Okay. This is first time I'm presenting in this Google Meet, so I don't know. Okay, let me find my presentation. Entire screen.
Right hand corner, bottom, you'll have present now.
Okay. Yeah.
You can present your presentation.
Okay. But where is my screen?
Manu, it won't show as your screen, so you give the present now. I had the same confusion as well because I use Teams as well. The thing is that you have to give present now, and then whatever is appearing, you have to just give share, and then basically whatever is on your screen will be shared. So it doesn't have separate windows. So whatever is shared, yeah.
No. What the heck? Just present window. Is it share? Can you see my slides now?
It has begun presenting, sir.
Do you see my screen now?
Your screen, but your slide is not visible, sir.
Yeah. You have to put up your slides.
Okay, this is.
You have to open up your PowerPoint window to show them. Actually. Yeah, if you open the PowerPoint, then I think it's solved.
Oh, so much difficulty. Okay.
Have your PowerPoint window open.
Okay, just a moment. Yeah, I'm opening it. Okay. This computer is slow. Okay, I open my PowerPoint now, and it's in full screen. Stop presenting. Oh my God, it's so difficult. Just give me a second. Let me fix it. Oh my God. Okay, present now your a window. Do you see now? Hello?
No. Yeah, I think it's starting to show. Yeah.
Yes, sir. The slide is visible now.
Now we can. Yeah.
Oh my God. Okay. So now you see in full screen, yeah?
Yes, sir.
Okay. So thank you for your kind introduction, and thank you for inviting for this webinar. I work as a postdoctoral fellow in Gothenburg University in Sweden. Gothenburg is in the west coast of Sweden. So I work in the University of Gothenburg in the Department of Molecular Biology. So in this talk I will be discussing the applications of ultrafast spectroscopy to unravel some of the fundamental biophysical process. My slides are changing, yeah? I don't have any control whether it's changing or not. Is it changing?
Yeah,
Yes.
basically what's in your screen, I think. Yeah.
It's changing, yeah?
Yeah.
Okay.
Yeah.
Okay, so before going to the talk, I would like to brief some of the basics of spectroscopy. So what we do that we in spectroscopy we study the matter using electromagnetic radiation. So the interaction of different part of electromagnetic radiation with matter will interact differently, and it will have and you can get a different set of information from that kind of interaction. For example, if you use infrared part of the light that causes molecular vibrations, whereas when you use visible or ultraviolet light, you can get information about the electronic transition between different energy states. So in this talk, I will be mostly focusing on these two different part of electromagnetic spectrum that exclusively used to study some of the basic biological process. Species across all the life kingdom of life uses rely on the ability to sense light condition. Some uses these light to trigger cellular functions, and some uses these to store energy in the form of through photosynthesis. So in the first part of this talk, I will be discussing one of these the process that triggers some cellular process. So this is one of the biomolecule which is called phytochrome, which are responsible for this kind of signal triggering is called phytochrome. So this signal triggering causes various physiological changes in this in the different organisms. So I will be discussing the structural dynamics of one of the phytochrome extracted from bacteria in the first part of the talk. So in the second part of the talk, I will be discussing the energy transfer primary energy transfer process in photosynthesis. In both of these process, I will be using ultrafast spectroscopy to study this process. So okay, one more thing I missed, that when the light, when this system, I mean this kind of, for example, phytochrome, use this light to induce some development in biological process. Biological process is that kind of process is known as photomorphogenesis. So okay, now we start with the first part of the talk. So this is the current project I am involved in here in Gothenburg. So as I mentioned in the beginning, the central theme is to understand the structural dynamics of a biomolecule called phytochrome. This protein has been studied by crystallography for many years, and most recently by femtosecond serial crystallography. So I mean, even there are a lot of studies. The many molecular details of this process is still missing. So I use ultrafast vibration spectroscopy to fill some of the missing details. So in the most of the time, a major time of my stay in Gothenburg, I spent to set up a nanosecond visible palm femtosecond mid-IR probe spectroscopy is set up to study the photocycle of a bacterial phytochrome. So in the left-hand side, this is a cartoon representation of that setup, which recently been featured in the front cover of a PCCP, a journal. Okay, this is a PCCP. Then the second project I am involved here is to study, to measure the femtosecond transient from the same bacteria to complement some of the structural changes found in this bacteria from serial femtosecond X-ray spectroscopy. And the third project I am involved to understand the ground state heterogeneity in this bacteria using two-dimensional infrared spectroscopy. So in this talk, I will be only discussing the first part. This part. The lab I am attached to mostly working on crystallography. I am the only person in the lab now doing spectroscopy. So this part, the last two part, I will not discuss. But for brief, here you can when you do this serial femtosecond X-ray spectroscopy, this is usually you need to go to the large facilities like a synchrotron facilities. So with that, you can. This is actually done in free electron facility. So in that method, using that method, you can see, you can take a snapshot of the structural dynamics of the system you are interested. The two-dimensional infrared spectroscopy is a bit complex. Third-order nonlinear spectroscopy, but it can give you a vast amount of information about the vibration coupling, diffusion, and chemical exchange. So now we briefly look what is a bacterial phytochrome. Phytochrome in general is a photosynthetic protein that found in nature. It can photoconvert between two metastable state known as PR and PFR. PR is the, according to their absorption maximum. If you look the absorption in PR is the red, and PFR is is far red. So that's how the name comes. So PR is the resting state, and PFR is the active, biologically active state. So the switch from PR to PFR is initiated by a light absorption at 660 nanometer, and in the dark it revert back to the resting state. This resting state can also be achieved by using a light photon at 750 nanometer. In the center, it shows the crystal structure of this bacteria in its resting state as well as in the light activated form. This structure is solved in our laboratory in few years before. So this bacteria has several domains. The chromophore, which is the biliverdin, which is like a tetrapyrrole chain, which is responsible for triggering these, initiate that triggering for the switching, can be seen here in orange color. Maybe it's very hard to see, but it's there. So the photo activation of this protein can be described in three stages, such as LumiR, META-R, and META-RC. The time evolution of each state can also be seen in this scheme. So in the center, actually, it shows the structure of this biliverdin chromophore. So what happens that when the light photon hit this chromophore, it will have a isomerization. So in the PR, it will be in one state, and in the PFR, it will be having a isomerization around the D ring to reach this when it's reached the PFR. So during these changes, there will be, these isomerization changes cause several vibrational changes inside the system. So if you track that vibration, you can get the information about the structural dynamics of these photoswitch. So since this is vibrations are changing, so if you look the infrared you can probe these with infrared light. So, there have been applied several ultra-fast vibration spectroscopy technique to solve this photo cycle, but none of them could completely resolve the entire photo cycle event. For example, when you use femtosecond transient absorption, you can only solve the, you can only track the initial events. Whereas when you use the step scan method, you cannot resolve the early events. So therefore, we applied a new experimental approach where we synchronize the nanosecond visible palm with the mid-IR probe pulses, which allowed us to follow the structural dynamics in nanosecond to millisecond time scale. This is on the left-hand side actually shows the crystal structure. Okay, so this is the scheme of that setup, which I built here to study this photocycle. Basically, it's a palm probe setup. In this method, what you do that you excite the system of interest with a narrowband light and probe the resulting changes in the system using a broadband light. So since here is we are interested to look the vibration changes. So the things are, the probe is in the infrared, in the mid-infrared region. So I have I excite the sample with a nano at 660 nanometer from a nanosecond laser. Then I use the output of a femtosecond laser at 800 nanometer to generate the probe and reference pulses. Then the pump and the probe pulses are focused at the sample position and especially overlapped also, whereas the reference pulse will be slightly offset. And the resulting signal from the sample is detected by a MCT detector. In order to keep the sample in its resting state, it is continuously illuminated with a laser at 780 nanometer. To avoid any kind of degradation in the sample, it continuously moved during the acquisition. So yeah, that's it about this setup. Okay, what I thought to say that this is the femtosecond laser I'm using. No, on the right hand side actually the actual setup of the lab. Here, this is the femtosecond system I use, which is actually using. It's interesting to maybe to mention that it's a regenerative amplifier which use the chip pulse amplification technique, which is the technique. In 2018, the Donna Strickland and Gerard Moreau got Nobel Prize. So this is the technique you can make the pulses with extremely intense, powerful pulses. And the other technique we have like a optical parameter amplifier, which using that you can tune, you can have the laser spectrum from the UV to far into the infrared. So this is, I think this technique came before the advent of dye laser, but is somehow not in application for several years. But after those times, I think dye laser was the choice to tune the laser. In my PhD, I work with one of the dye laser. The problem with dye laser, you have to use all these nasty dyes. So then later this OPA got, very, like a now it's a choice to make to tune the, if you want to tune the laser different frequencies, it is best choice. Okay, that's anyway just about the technique. This is the scheme shows how I achieved to track the kinetics changes over 6 orders of magnitude. This I will not go to the detail, but the key is here is that you have a the key is the repetition rate of these pump and probe pulses. So between 2 consecutive pump events, you have a 15 milliseconds of time duration, which is enough to track the complete photocycle of this bacterial phytochrome, which I'm interested. So the basic thing what I use that I use an electronic delay generator to obtain the early delays between the pump and probe from minus 50 nanosecond to 150 microsecond. So the late delays are obtained by calculating the signals of 20 consecutive probe shot after the nanosecond pulses. We can discuss this if someone interested to. This in detail. So there exists a controversy about the photocycle state of the bacterial phytochrome. So the new technique applied allowed us to track a new intermediate state in the photocycle of this bacterial phytochrome. On the left-hand side, it shows the resulting spectra. When you analyze the recorded differential spectra, after analysis, you can get this kind of spectra. So in this spectra, the new intermediate, what we found is in the black color, which is similar to the Lumiere state, which is in the red color. But the new intermediate state forms before the original Lumiere, and because of its spectral similarity, this new state is named as early Lumiere, and the original Lumiere state is named as late Lumiere. The spectral evolution of that two state in this frequency between these 1700 to 1725 can seen in the inset. The time evolution of every state can also be seen here, and the concentration of that whole state can also be seen here. On the right-hand side is the photocycle scheme of this bacteria with the modified photocycle state. So this is all about my the first part of the talk. What is the time? Do we have still time? Yeah. Okay. So maybe then I can discuss the second part. So, okay, the second part is about photosynthesis. Okay, the primary process of photosynthesis. So, as you know, in photosynthesis, you reduce carbon dioxide using the electron from water in the presence of sunlight to produce biomass and oxygen as a waste product. The annual rate of energy captured by photosynthesis is immense. It's almost 6 times larger than the energy consumption by human civilization. So if you look for a clean, abundant, and reliable energy source, photosynthesis is a great place to start. we more often we are familiar with photosynthesis by plants. On the right hand side actually shows the habitats of photosynthetic life form. So there are some species they can, other than plants, they can also perform photosynthesis quite well, such as some photosynthetic bacteria and algae. So in this talk, I will be discussing the primary photosynthetic process in photosynthetic bacteria called photosynthetic purple bacteria, which lies in the bottom of a lake, pond, or streams. It makes its life with the solar spectrum concentrated in 500 nanometer and 800 nanometer region. Because why? Because the other part of the spectrum is filtered in the water by algae and above the water by the plants. So they have to make their living with these two spectral region. So this is electron micrograph of a thin cell section of a photosynthetic purple bacterium species called Rhodobacter spheroides. Here you can see like a small round-like thing, which is called chromatophore, which equipped with all the pigment protein complex that required for photosynthesis, so that they can perform photosynthesis independently. So in the center, it is the atomic structural model of this chromatophore, where all the pigment protein complex are distinguished. The light harvesting complex 2, shortly LH2 in green color, and light harvesting complex 1 in red color, which shortly called LH1, and the reaction center in blue color. Together, the reaction center and the LH1, known as the core complex, the reaction center and the associated light harvesting complex forms a functional unit called the photosynthetic unit. The ATP synthase in yellow, and the cytochrome BC1 complex can be seen in purple color. So on the right hand side is the absorption spectrum of this chromatophore. So as I mentioned before, that these bacteria has to make their living using the light spectrum at 500 nanometer and 800 nanometer region. The 500 nanometer region is taken care by the pigment called carotenoid, whereas the 800 nanometer region is taken care by bacterial chlorophyll. If you look the absorption spectrum carefully, it's very impressive that the spectral and spatial arrangement of this system, this way that the LH2, these green ones which absorb at high energy, is placed at the periphery of the system, compared to the core complex, which absorb at a low energy. The maximum comes at 875 nanometer. This actually helps the system to funnel the energy into the final trap, that's to the reaction center. So when a light photon comes, it immediately absorbed by the antenna complex and immediately transferred to the reaction center, where the chemistry starts. It's a very ultra fast process. However, some of the energy is still lost during this process. So this lost energy will be in the form of fluorescence. So by examining this fluorescence signal, you can get the information about the mechanism and dynamics of the primary process of photosynthesis. So all in this study, I used fluorescence spectroscopy to understand this fundamental process. This is like a summarized the process involved in the bacterial photosynthesis towards energy production. But in this talk, I will be only talking about the process up to the charge separation in the reaction center. So as I mentioned in the beginning, these bacteria lives in a place where it's a less advantaged ecological places they are living. So the structure and the associated spectral features of these bacteria has to be very versatile to be successful in that condition. So the recent atomic structural analysis from these bacteria shown that when the bacteria grown in different light condition, its structural organization is changes. So that was the first aim of this project, that to understand the impact of the available number of antenna size on the excitation energy migration rate and the efficiency of the trapping of these absorbed photon at the reaction center. And now coming back to this chromatophore again, the constituent units, that is the LH2 and the LH1. If you look the LH2s between different species, their structure are almost consistent. It's similar. Whereas the structure of the core complex, that's this one, changes species to species. In these species, there are two types of core complex coexist. A majority of a S-shaped dimeric core complex, and a C-shaped, a minor C-shaped monomeric core complex. So that was the second objective of this project, to understand the impact of the design of the core complex on the energy transfer rate and the trapping of that energy in the efficiency of trapping that energy in the reaction center. So in order to solve this objective, in my collaborative laboratory, they prepare the sample at a different light condition. So in this graph, it shows the two representative absorption spectra of two samples grown at two different light conditions. On the top, it's the sample is grown at a high light condition, and the bottom is the sample is grown in the low light condition. The structure of this chromatophore is schematically presented in the insert. So here the green dot represent the LH2, that's the peripheral antenna, and the red one is the LH1, the core complex. So when the system grown in the high light condition, the available number of LH2 is less, whereas when the system grown in low light condition, the number of LH2 is more. So the absorption spectrum is decomposed into the constituent spectra, that is LH2 and core complex. That helps us to get the LH2 to the core complex ratio. So in order to solve the second objective, we produced a sample contain either only monomeric core complex or only dimeric core complex with controlled levels of LH2 complex. Okay, so as I mentioned before, the main experimental technique was used fluorescence spectroscopy since all this process happens in very fast. So we need to resolve that process that can only achieve through time resolve method. So in this method, we are used different kind of detection systems. One was using streak camera, which can resolve very fast events to picosecond resolution. I mean, like a sub-picosecond resolution. And the other method was used time correlated single photon counting, which is good when you are looking for like a process between 10 to hundreds of picosecond to nanosecond process. On the right hand side is representative the kinetic trace from this bacteria in green color, and the black one shows instrument response function, which tell you this is, I mean, the instrument response function is the limiting factor to resolve the kinetic process. By doing some deconvolution, you can go maybe up to you can get 10 times. You can trust on the kinetics up to 10 times lesser than the instrument response function. This is the integrated lifetime obtained from this one of the chromatophore at different light intensities. So you have to consider two states. One is the active state, which you can where the measured lifetime will be very short term, whereas in the saturated case, the measured light will be longer. So in context of this the photosynthesis, how it was. So in the active state, that is a low light intensity case, all the absorbed energy will be immediately transferred to the reaction center and is immediately trapped in the reaction center, which correspond to a shorter measured lifetime. So what happens that when you increase the light intensity, more and more photons will be absorbed, and most of the reaction center will be, oxidized, and it comes to a situation where the reaction center is closed and it cannot process immediately another one. So that will cause elongation of the recorded lifetime. So in the center is a place where the time corresponds to a mixture of open and closed reaction center. So these graph shows you the integrated lifetime from the sample having different amount of peripheral antenna complexes. These lifetimes are only shown in the active state or in the saturated state. So irrespective of the state of the reaction center, when you go from the system having less number of peripheral antenna, that is LH2, to the more number of LH2, the measured lifetime will increase. So this can be achieved, thought of two extreme case. So in the minimum case where there is the system that doesn't have any peripheral antenna, which shows a very short lifetime, and when the system having more number of peripheral antenna, it will correspond to a elongated lifetime. So this is the efficiency of energy trapping inside this reaction center from the sample having different set of peripheral antenna complexes. So this quantum efficiency is nothing but that this is the probability that an absorbed photon leads to a charge separation in the reaction center. So in both case, in most of the case, the efficiency is over 80%. So which decreases when you go. I mean, when you increases the number of peripheral antennas, and these decrease will become more drastic in case when you have 800 nanometer excitation compared to the 900 nanometer excitation. So this can be thought in this way that in 800 nanometer, the light will be absorbed by the peripheral antenna, then transferred to the core complex and to the reaction center. Whereas in case of the longer wavelength excitation, you immediately exciting the core complex, and the number of steps will be less, so that the system, I mean, the energy can immediately trapped. So that that corresponds to the higher value in efficiency. So this is this figure scheme summarizes the objective of the second project, that to understand the impact of the structural organization of the core complex on the efficiency of the energy trapping. So this is the system where you have a dimeric core complex, and this is the system you have only monomeric core complex. So when you look the decay, emission decay, you can immediately see that irrespective of the reaction center state, the measured time is shorter in case of system having a dimeric core complex, whereas in case of monomeric it's longer, and it's more substantial in case of saturated photosynthesis. The difference becomes 2 times. These can be the physical reason behind this is not quite very clear, but this can be thought of that in case of dimeric core complex, you have access to 2 reaction centers simultaneously that might enhance the this energy trapping process corresponding to a shorter lifetime. So this is the quantum efficiency found in the system having dimeric and monomeric core complexes. So similarly, like in the previous case, with the different levels of LH2 contents. So the efficiency is slightly higher when the system having dimeric core complex compared to the monomeric core complexes. So with that, I would like to conclude that in the first first part of the talk, what we found that we used a new kind of spectroscopy technique that allowed us to study the photocycle events from a bacterial phytochrome, and we found a new photocycle intermediate in bacterial phytochrome. And from the second part, it is this study shows that the robustness of these photosynthetic bacteria that function surprisingly effectively in wide variety of environmental conditions. So with that, I would like to thank my colleagues at different places and my funding agencies. This is my present team. This photo was taken last summer. One of our colleagues was leaving the group. Thank you for your attention.
Participants having doubts can post in the YouTube chat.
Sir, I have a question.
Mm.
The photosynthesis process that is taking place in plants above the ground and
Yeah.
plants that are found at the bottom of the ocean, would they be following the same processes?
Yeah, I mean, the process will be, I mean, generally similar. I mean, but the structural unit they have is completely different. In bacteria, is much simpler. That's why we took that as a, I mean, like a probe. Yeah.
Okay, but what about algae, sir? The blue-green algae that is found, and that on, let's say, the ocean surfaces.
Algae, I think there will be, I mean, the bacteria what I studied is anoxygenic because, I mean, it cannot, I mean, it won't release oxygen. But I guess algae will be oxygenic. So it is more like in a plant, their structural composition. Yeah.
Thank you, sir.
No problem.
Thank you, sir. I request Dr. Rosebindu Joseph, Associate Professor, Department of Science, to render the vote of thanks.
A very good evening, everyone. It's my great pleasure to propose a vote of thanks on this occasion to our speaker, Dr. Manoj Chenchilian. On behalf of the Department of Science and the entire CAS fraternity, I extend my heartfelt thanks to Dr. Manu, who took his valuable time out in this busy schedule to speak with us. I must mention our deep sense of appreciation for Dr. Manu and his research work. We hope to keep up our association with you, sir, in the future. Thank you. Thank you very much.
Thank you for your kind words.
Thank you, sir. Thank you, ma'am. I invite Dr. Mandira Mohabatra, Assistant Professor, Department of Science, to introduce our third speaker, Mr. Venkata Krishnan Bharadwaj.
Good evening, everyone. I take the privilege to introduce an enthusiastic and innovative person, Mr. Venkata Krishna Bharadwaj. His passion is science, and he believes that knowledge shared is knowledge gained. He completed Masters in Physics from Bonn University, Germany, and then served as research assistant at the Mulliken Center for Theoretical Chemistry, Bonn University. At present, he is pursuing doctorate degree at the JGU Mainz, Germany. The thesis during Masters, titled Circuit Theory of Multiple Pair Resonances in 3 lead superconductor devices, was widely acknowledged. During the tenure as research assistant, he dealt with trajectory analyzer and visualizer. He completed multiple intensive programs, including the topics like simulation of icing model, interferometry techniques, multi-impurity Anderson model in generalized geometry. Moving on to the awards received, he is the recipient of Amidex Scholarship awarded by the Academy of Excellence. Also, the recipient of Bonn International Graduate Studies Scholarship awarded by Bonn University. And when he was in BSc, he was the recipient of Inspire Fellowship by the Department of Science and Technology, India. He has actively participated in poster as well as oral presentations in multiple conferences like DPG Spring Meeting, which is the annual German Physics Conference, also the Joint European Magnetic Symposia, Germany. Last but not the least, he is professional handball player, having represented the Karnataka State Federation 9 times at national level tournaments, a passionate mridangam player and violinist, and also a professional chess player having represented Karnataka state at multiple tournaments. We are privileged to have such a dynamic personality among us today. Sir.
Hello?
Yes, VK, you're audible.
Can you hear me? Thank you very much, ma'am, for a very kind introduction. So let me share my screen now. Brian, let me know if my presentation appears.
Yes, it is visible.
Okay, good. Great. So thank you everyone for patiently waiting till so late in the afternoon. Let's start with the topic of my seminar today, which is Spintronics, and which is basically exploiting the dual personalities of the electron so as to use them as alternatives for information storage. Okay, so the outline would be, I'll give you a helicopter view of spintronics, basically starting from spin on the electronics and then spin-dependent scattering, followed by giant magnetoresistance, and which will be discussed in detail, but then we'll talk about MRAM and other applications in spintronics, and then we'll briefly look at different frontiers of spintronics. Followed by which the second part will be on magnetic skermions, which is my area of research, where I'll introduce different magnetic textures, generation of so mentioned magnetic skermions, then skermion racetrack memory, and basically I'll then conclude with the summary. So I am doing my PhD in Johannes Gutenberg University Mainz, located like half an hour drive from Frankfurt. And the university is of course named after Johannes Gutenberg, who invented the printing press and the famous Gutenberg Bibles. And our university is home to around 30,000 students, spanning with all kind of research activities in different areas of sciences. And this is basically my group, which is a combination of Inspire group led by our professor Jairo Shinowa and our group leader Kari Nevash-Osite, who is my PhD supervisor, who is the head of the twist amino ether group. Okay, so the PowerPoint is stuck. So let's start why we are even talking about spintronics. So this is a graph which was published in a 2011 article where representing as a function of time the amount of data that was analog compared to the digital. So the orange color is basically the data that was analog, which was in different formats like book, newsprints, photos, negatives, audio cassettes, and everything. And then this blue part is what is the digital, which is camera, mobile, CDs, hard disk, video games, floppy disks, and etc. So as you can see, from since 1986 to 2000, in the span of mere 20 years, majority of the information has changed from digital analog to digital, which means that there is a huge advent of technology which is going towards everything becoming digital, and we are reaching a place where we need better ways of storing memory devices, and also lowering the current and energy needs to store the information data. So to this end, we will look for other alternative ways how we can better our technological methods to store them. So let's start with asking ourselves a simple question: what is spin? So we all know that electrons have an inherent property, which is charge. And we know that based on this charge property of electrons, we have built all the semiconductor devices using capacitors, which store certain amount of electrons as charge. And based on that, we have basically build different kind of electronic devices. It so happens that electrons also have another interesting property called spin. And spin is a spin of an electron is a fundamental quantum mechanical property, which is in a way, in a classical analogy, we can say it as an inherent rotational sense. But this classical analogy only goes far because the electron is a quantum mechanical particle, and a point particle, so there is no sense in thinking of it as an electron spinning on its own. But it's just a classic analogy. But it's a fundamental quantum mechanical property which takes only two values, either plus half or minus half, which is enough for us to define two different ways of storing information. So based on the charge property of electrons, we have built transistors, which has been the bedrock of all the memory devices like flash memory devices like DRAMs and solid state drives like SSDs, which store information on your computers and laptops. But it happens that using spin property of electrons, we can also build memory devices called magnetic memories, which is already in use like hard disk drives, or these days we can start using something called magnetic random access memories, which is basically using the spin property of the electrons. And this field of technology where we try to exploit, where we are exploiting the spin property of electrons to develop memory-based applications and information storage devices is the field of spintronics. Okay, so let's start with some fundamental principle to understand spintronics in detail. So let's start with spin-dependent scattering. So here on the upper figure, what I have is the blue color is a ferromagnetic layer where all the spins are pointing to the right. And the top layer is another ferromagnetic layer where all the spins in this ferromagnet are pointing to the left. And in the middle, the yellow colored layer is a non-magnetic layer. So when we pass an electron, which contains basically unpolarized current, which means that there is equal number of up and down electron spins, when we try to pass them, the resistance of the material depends on the nature of the spin. So the electrons that are flowing, the blue kind of electrons where the spins are pointing down, which are flowing in the bottom layer, encounter less scattering compared to when they flow in the top layer. Similarly, the red electrons, which are basically these electrons with spin pointing upward, when they are flowing in the red layer, they encounter less scattering compared to when they are flowing in the blue layer. And in the yellow layer, since it's a non-magnetic layer, both up and down electrons basically have the same amount of scattering. So based on this, we can see that the resistance to the flow of electrons depends on the spin orientation of the ferromagnetic layer. So when you compare this to the bottom figure, where both up and bottom layer of the ferromagnets both spins are pointing in the same direction, we see that the total resistance across this sample is lower than this sample. So which is basically to say that if you have a multi-layer of ferromagnets separated by non-magnetic layers, the resistance depends on whether the ferromagnetic layers are aligned in the same direction. So the spin plays a huge role in deciding the nature of the resistance. So based on this, which is basically the effect described as giant magnetoresistance, which got Nobel Award in 2007 for the works from Albert Fett and Peter Grunberg, Albert Fett from France and Peter Grunberg from Germany, where they built an iron and chromium alternative layers where they measured by stacking multiple magnetic layers separated by non-magnetic layer, which are shown in yellow, and the ferromatic layers here shown in red. So when they measured the resistance when the ferromagnetic layers all having the spins in same direction, in contrast to that of when the alternative ferromagnetic layers have spins in the opposite direction, they saw that there's a huge bump in the resistance. So which is basically called the giant magnetoresistance, which was approximately around 10% increase in the resistance, which was measured at 4.2 Kelvin at very ultra low temperatures. But this genesis of giant magnetoresistance made a huge impact on the development of spintronics. So the effect of giant magnetoresistance occurred, gave birth to something called magnetic tunnel junctions. So before we discuss that, we can already see that this was basically your hard disk drive in 1962, which was built by IBM, which was around 24-inch in diameter, these magnetic disks. And this total device was only a capacity of 28 MB. But today, in the pocket size, we have the same device which can hold 1 to 10 terabytes, which is merely 1/10 of the size. And basically, this is approximately around 8 orders of magnitude decrease in the size of storing magnetic data. So this already shows that the spintronics field has developed so far since the discovery of giant magnetoresistance. It is worth exploring alternative ways of using spin. Okay, so let's discuss one of the applications which uses giant magnetoresistance, one of them called magnetic tunnel junctions. Magnetic tunnel junction is basically two ferromagnetic layers separated by an insulating dielectric material. So the physics here is a little bit different in the sense that when an electron passes from a conducting ferromagnetic layer to the other conducting ferromagnetic layer, since this is an insulating dielectric material, basically electrons tunnel through this insulating layer. And the probability of the tunneling basically depends on whether the second ferromagnetic layer is aligned in the same direction as that of the first one. So for example, here in the top image, the spins in the left ferromagnetic layer are pointing to the right, and also the second ferromagnetic layer, the spins are pointing in the same direction, and the probability of tunneling is more for the red electrons to the empty states in the right conducting layer than that of the blue electrons. But in contrast, if you look at the bottom image, the left one is the spins are polarized in one direction, and on the right image, the spins are polarized in the another direction, which means that now the tunneling probability has reduced, which means to say that the amount of electric current or the voltage which you would measure across the sample would be lower in the bottom one than the top one, where the spins in both the layers are aligned in the same direction. And these magnetic tunnel junctions have huge advantages because they basically act as a resistive element in your circuit. Depending on the direction of the spins, they either measure low current or high current, which can be used to decide whether your memory stored is in 0 or 1 format. So one of the devices that uses this magnetic tunnel junctions as a resistive element in a circuit is called MRAMs, which is basically magnetic random access memory. So the magnetic random access memory looks like this. So what you have is a series of conducting strips which are stacked in like a grid here shown here. And between these horizontal and vertical strips, what we do is we put these magnetic tunnel junctions, between the layers. Now when we pass a very small current let's take for an example in the middle strip, and also now measure the voltage across the first green strip, then we measure the voltage across this magnetic tunnel junction, which is a resistive element. Now, depending upon whether the spins in the magnetic tunnel junctions of two layers are parallel or anti-parallel, the measurement of your voltage differs. If they are parallel, then you would measure a higher voltage. If they are anti-parallel, then you would measure a lower voltage. So this basically tells us the orientation of the spins in the magnetic tunnel junction. Now, it was shown that by just passing very ultra low currents, we are able to measure the spin orientation, which is basically telling you that you can store your information as the orientation of the spins in your magnetic tunnel junction. Now, if you pass in the same electric bit line and a very high current, you can also shift the spins of one of the magnetic layer, which means that now if you pass a very high current, the spin orientation in the fixed layer on the bottom layer will be now shifted into the blue color, which means the spin is shifted into the other direction. Now, this is basically a way of writing memory into the system. So when you are reading, you pass a very low current, and based on the resistance, you can read which orientation of the spins are in your magnetic resistive element. And if you want to write new information into your magnetic resistive elements, you just pass very high current, and they basically flip the spin direction, and you can write new information. And this is basically how an MRAM works. And it is very interesting to know that very recently in October, Sony revealed that they are hiring the company called Evaspin Technology to build MRAM memories into their electronic devices. So MRAM memory is not anymore just a theoretical concept. It is already being used, beginning to being used in industrial applications. Sony is already using, and there are other companies, for example, IBM in 2020 announced that they have 14 nanometer MRAM chips, which is a huge development in terms of magnetic memory devices. Okay, so now that we know how we can use giant magnetoresistance to use magnetic tunnel junctions as MRAM chips, let us look into other different areas of spintronics, which I'm not going to go into detail, but it is good to know that it's not only ferromagnets, but there are other areas in spintronics. So let's start with antiferromagnetics, which is basically, so far we were discussing the cases of ferromagnets where the spins are all pointing in the same direction. But in an antiferromagnet, you will have spin up, spin down, spin up, spin down in alternative fashion, and there is no net spin accumulation. For a very long time, it was thought that antiferromagnets are not very useful for storing information, but recently a lot of works have been shown that antiferromagnets have a lot of technological advantages over that of ferromagnetics, and antiferromagnetics is now becoming a new emergent field in the field of spintronics. Then there is another field called spin calectronics, where we use the transport of heat through the system to effectively transport spin current. Basically, it is called spin Seebeck effect and other effects, where we use the heat transport in the system to also transport spin. And there is a field called magnonics. Magnonics is basically a field of spin waves, where magnons are the fundamental excitations of spin, just the way photons are basically the excitations of the electromagnetic field. Magnons are the excitations of your spin wave or of the spin fields. And these spin waves are also have a huge technological advantage because they operate at high frequencies. And since they only transport spin, they don't transport any charge. So there is no loss of energy because of the resistance, because it's only spin information which is carried. And then there is area of superconducting spintronics, where we use multi-layers of superconductors and ferromagnetic layers to infuse superconducting behavior into your ferromagnetic layer, and vice versa, and interesting properties arise. And that is another field of spintronics. And then there is an area of topological materials, where materials having topological properties which can influence the transport of spin and current in your materials, which have unique stability and very interesting properties. Then there is another field which is called heterostructures, where we have different materials basically multi-layered onto each other. For example, a ferromagnet and an antiferromagnet multi-layer, or a ferromagnet and a superconductor, or a superconductor and an antiferromagnet. And these heterostructure properties have very interesting properties at the interfaces. So spintronics is basically a very emerging new field, which is creating a lot of subfields and has huge potential and opportunities for a lot of technological applications. Even though spintronics started as a field for finding alternative ways to store memory, it's been shown that spintronics is now much more than information storage, where we can use it for computing devices, we can use it for reservoir computing, where we can use for logic, spin logic systems, and much more. So this is basically, in brief, what spintronics is all about, where we exploit the spin properties of the electrons to do all kind of technological applications. Now, moving on to the second part, which is magnetic skermions, which is another part of Spintronics and my specialization in my PhD. So let's begin with looking at some magnetic textures. So let's start with a magnetic domain wall. So what is a magnetic domain wall? So magnetic domain wall is basically a wall separating two different areas where spins are pointing in different directions. For example, in the blue area, the spins are all pointing in the up direction, and in the red area, the spins are all pointing in the downward direction, and there is a smooth transformation of the orientation of the spin from left to right, and hence there is a magnetic domain wall. If you look at the same structure in 3D in a material with cylindrical symmetry, we see that it gives rise to a topological texture called skermion. And the skermions are basically the texture of a skermion looks as follows. At the center of a skermion, the spins are all pointing in the down direction, and far away from the center, the spins are all pointing in the upward direction. Now, from center, if you go along the radial direction, then the spins are gradually turning towards from down to up and in the other direction. So if you start from an extreme left, it starts like this and then goes like this and then comes up. So that's basically, if you take a cross section along the center, along the x-axis here, this is basically one domain wall. But in a skermion, it is so that the domain wall is in 2D, which means any radial direction, it's a domain wall. But skermion also is very special because it's a topological texture. What do I mean by this? So let's look at this in bit detail. So the magnetic skermions is also already observed in bulk materials like magnesium silicide. So the experimental observations were done using neutron scattering experiments, where they observed a 6-fold symmetry which indicated the presence of skermion lattice. And also in 2010, there was observed in a real space imaging of magnetic skermions using Lorentz electron microscopy. And magnetic skermions have a hedge-like texture, which means that the spins from the center are all pointing in the outward direction or all pointing in the inward direction. So why are magnetic skermions interesting? Why do we care? So to answer that, before we answering why magnetic skermions are interesting, let's go back and look at some interesting properties of domain walls. So it so happens that if you have a domain wall in your sample, when you apply an polarized electric current, it can move the magnetic domain wall. So why is the simulation not working? Okay, so when you now apply an electric current through your sample, which has a domain wall, the domain wall starts moving. So the reason why it happens is because of the following. So when you apply an electric current, so you have spins like this in a domain wall, pointing in this direction and slowly turning into this direction, which is basically an 180-degree domain wall, right? Now, when you send a polarized electric current, there is an exchange of angular momentum, spin angular momentum from the conduction electron to the spin in the sample. And this, due to conservation of angular momentum, even though when a conduction electron passes through a ferromagnetic material, it tries to realign its direction as it moves in the direction of the spin in the material. But we know that due to conservation of angular momentum, part of the angular momentum is transferred back into the material, which basically then starts rotating the spins in your sample, which is basically saying that your domain wall is moving. So that is why when you apply an electric current, spin polarized electric current through a sample having a domain wall, now the domain wall starts moving. Now, using this property that you can move domain walls using electric currents, Stuart Parkin in 2008, who was an IBM researcher at the time, proposed a very innovative idea of application device called racetrack memory, which is application device is to store memory in form of a racetrack. The reason why is it called a racetrack is as follows. So if you look at what is happening in a racetrack, it's a thin nano strip of a ferromagnet, and now it has series of red and blue regions separated by domain walls. So each region represents 0 or 1. So if it's pointing in one direction, it is a 0. If it is pointing in another direction, it's a 1. Now, when you apply current, the domain wall starts to move, which we just saw. Now, what we do is we fix the nanostrip, and we basically keep reading element or a writing element at the bottom. And when the domain wall starts moving, we basically read the direction of the spin in the nanostrip. So whenever the red region passes, we know which is the direction because of the measurement of the voltage, and whenever the blue region passes, we measure the other direction. So basically, by moving the domain wall, we can basically store and read and write information. And since it looks like we are running them through a nanostrip at very high velocities, which is approximately in terms of 100 kilometers per second, hence it's called a racetrack memory, which is basically because here the information which is running along the racetrack, not the physical device. In contrast to if you have your hard disk, that is your hard disk in your laptop or computer, you know that there is series of disks and there is disks which are always running. Hence, you have you can identify when their hard disks are running. You can identify them by hearing the noise. But here, no physical device is moving. It's just the information that is moving along a nanostrip. Hence, racetrack memory. So this domain wall racetrack memory can also be extended to skermions. Instead of having the alternative red or blue regions which are separated by domain walls, what we'll have is basically magnetic skermions. So in 2017 and 2013, in 2 papers, they proposed the idea that we create a series of magnetic skermions and we pass them along a raised nano strip, just like we passed a domain wall. Now, the presence or absence of a skermion basically tells you if you have information in this one direction or the other direction. So this is possible because we can controllably produce magnetic skermions when we want and switch off when we don't. So for example, if we switch off the current, then we don't produce a magnetic skermion. So then we detect this as a 0, and whenever the skermion passes, we detect as a 1. And why are racetrack memories better than skermion racetrack memories better than domain walls? Because it so happens that the amount of electric current that you need to spend to move a domain wall in comparison to skermion consumes almost 1/1,000,000th of a current. So it is order of 6 energy consumption better. And also it happens that these magnetic skermions have topological stability because of their inherent structure they possess. Now, the question we ask ourselves is magnetic skermions, is that all that can do? Can we only observe skermions in one kind of magnets? So to explain this, let us look at 2 different kind of magnets. One here on the left is we call PMA magnet because the spins in this magnet are all pointing in the direction perpendicular to the thin sample, which is called perpendicularly magnetized, perpendicular magnetic anisotropy magnet. And on the right is shown in the green color is where the magnet where all the spins are pointing in the plane along the x direction, which is called the in-plane magnet. From this point on, if you have a blue color, it means that spins are pointing in the up direction. If you have a red color, spins are pointing in the down direction. And if you have green color, the spins are pointing in the x direction. Okay, so now we've seen the skermion, where in the center, the spin direction is pointing in the downward. And far away from the skermion, spins are pointing in the upward direction. So this is the color code. And if you take the same skermion and you put it in an in-plane magnet, then it would look like this. What you do is at every point on the skermion, you rotate around the y-axis by 90 degrees. So what happens is that the spins which are pointing in the z direction now will point in the x direction, and the spins which are pointing in the minus z direction will now pointing in minus x direction. So everything is rotated around the y-axis by 90 degrees. So in a skermion, in an in-plane magnet, now would look as follows. The spins are at the center are pointing in the minus x direction, and far away from the center, the spins are pointing in the plus direction. And from once you move from radially outward from the center, the spins gradually rotate from minus x to plus x. Okay, and this the work on skermions in in-plane magnet was published in our work in the last year, in physical review B. So the question we ask is, what kind of interactions in a magnet can lead to these kind of interesting magnetic textures? So we start with the first one, which is exchange. So exchange interaction is basically the one interaction which prefers all the spins in your magnet want to be aligned parallel to each other. And we call this exchange interaction. The second interaction is anisotropy. So what anisotropy prefers is that if you have a crystal, your spin should be pointing in the direction which it, in one direction which it prefers. Hence, it's called anisotropy. Because when you don't have anisotropy, the spins can point in any direction, right? But now, if you break that symmetry, then you choose that we want it to be pointing only in one direction. Then we call it anisotropy because now it spins only point in one direction of your specific choosing. Now, when you apply magnetic field, what does the magnetic field do? Magnetic field tries to align all the spins in the direction of the applied field, which is called Zeeman field. So if you have a spin in this direction and you now apply magnetic field in this direction, then the spin gradually rotates itself in the direction of the magnetic field. So that is called Zeeman field. And finally, there is another very interesting interaction called Zolesensky-Moria interaction, which is the reason why we have skermions, which basically prefers to the neighboring spins to point perpendicular to each other. So it is this balance of these four kind of interactions which gives rise to the balance of these interactions which gives rise to the formation of skermions. Okay. Now, we heard a lot about skermions. Now the question is, can you produce them? So it so happens that we can produce skermions in a very simple method. So what we do is we take a very thin sample, okay, and then everywhere in the sample, the spins are pointing along the plus x direction, which is shown in green. But at a very small spot in the sample, which is an inhomogeneity, the spins are pointing now in the plus out of the plane, plus z direction. So everywhere in the sample, the spins are in the x direction, but at the inhomogeneity center, the spins are pointing x direction. Now, if you try to pass the current through this inhomogeneity, it blows skermions. It tries to shed skermions out. And this is basically called shedding of skermions. So as you can see, it tries to expand the region and then it sheds skermions. And we show that by applying current pulses in a periodic current pulses, we can produce them as a train of skermions, which is important if you want to have racetrack memories. If you remember a couple of slides before, I showed you that we want to have skermions whenever we want, and we switch off whenever we want. So if you switch off a current, then suddenly the skermions disappear. And if you want to produce skermions periodically, you just apply periodic pulses of current. And it was shown that this was possibly done through our simulations. Then there is another interesting property of skermions. Because they have a very interesting texture, which is the topological stability. Just like a football, when you kick the football, you can make sure that the football not only goes in the direction of the where you kick, it also can spin in the perpendicular direction, which very famous score by Robert Carlos in the World Cup from the Brazilian team. You see that he makes sure that even though the ball intends to go straight, it also goes perpendicular to the direction, right? So it happens that when you apply current to these skermions, they also behave the same way. They not only, if you have a skermion and you apply current in this direction, they not only move in this direction, they also move perpendicular to the direction, which is basically called skermion Hall effect. So when you apply current along this direction, the skermion also moves perpendicular to this direction, which was shown experimentally a couple of years back. And this is not really good for skermion racetrack memories because you have a thin nanostrip and you're trying to move skermions in a straight line. But now if you see that the skermions also tries to move perpendicular, which means it start hitting the boundaries, they then get destroyed. Which means that your information is getting destroyed. And that is not good for a racetrack memory. But it happens that if we try to do this skermion motion instead of a perpendicular magnet where the spins are pointing in this direction, if you try to do the skermions in an in-plane magnet, this property is eliminated. So in which case, the skermions only move in one particular direction. So no matter the direction of the current you apply, the skermions always move in the unidirection, which means that now if you just build your racetrack nanostrip along this direction of motion, then you have a skermion racetrack memory. which is what we showed in our work. So to summarize about matrix skermions, we showed that you can produce periodically the matrix skermions so that you can use them on racetrack memories. And in contrast to the normal skermions, these in-plane skermions have unidirectional motion, which means that they always move in a straight line, which is a very technological advantage for racetrack applications. So my take-home message from today's my talk about Spintronics is that Spintronics has been a very successful story in the past 2 decades since its GMR genesis, where it has moved from fundamental science to an application-based science. And a lot of information storage-based devices can be built based on the magnetic degrees of freedom rather than charge degrees of freedom alone. And it also happens that the Spintronics is not only used for information storage, it can be used to do spin logics, like you do logic with capacitors. It can be used for neuromorphic computing, which is basically trying to mimic what a brain can do. It can be used for stochastic computing and much more. So exploiting the spin properties of an electron has much more advantages than using just charge degrees of freedom. With this, I would like to conclude my talk. Thank you.
Participants, if you have any doubts, you can post it on the YouTube chat.
Thank you, Vicky, for the talk. I have one question.
Yeah.
See, in general, it is told that if you have a regular hard disk and if you swipe it in between a strong magnetic field, the data can be erased.
Yeah.
In case of Spintronics, how does that work? Will the data be secure?
Okay, so even if you have a capacitor, for example, let's compare it to a charge-based device, and then let's look at how it works. How stable are the magnetic memories? So charge-based devices, so if you use a magnet and wipe it, nothing happens. But you can also wipe memory from a charge-based device like your RAMs by just applying electromagnetic pulse. So it basically destroys all the memory stored in it. So whether you use what kind of method to store information is irrelevant if you have a powerful method to just wipe the information storage. The reason why when you wipe a magnet on a hard disk, the information is stored because the information is stored as the spins pointing in up or down direction in a magnetic memory disk. And if you now put a magnet and wipe on it, it basically tries to align the entire magnetic film in one direction, which means that all your combination of ones and zeros will be now all ones or all zeros. Hence, your information is stored. So it's not the question of whether you can make them stable, yes, but to a certain extent, because we know that even if you just heat your hard disk, we can lose the memory because heating a sample loses the magnetic properties, right? So yes, you can always destroy memory by using a powerful magnet, but the question is, do we want it?
Okay, thank you.
Thank you, sir. I request Ms. Gayatri Mohan KV, Assistant Professor, Department of Science, to render the vote of thanks.
Thank you, Anna. Good evening, all. Respected Reverend Father Dr. Babu Paul, Principal Kayas, Reverend Father Anthony, Vice Principal Kayas, Dr. Sangeeta George, HOD Department of Science, our most valued invited guests, my colleagues, and my dear students. It's my privilege to have been asked to propose a vote of thanks on this occasion. I, on behalf of Department of Science, Kayas, and the entire fraternity of science here, and on my own behalf, extend a very hearty vote of thanks to all the speakers for gracing your important work and sharing with us your findings and opinions today. I would like to thank all our speakers who readily agreed to be a part of this international webinar despite their busy schedule. A big thank you to Dr. Krishna Kumar C for his effort towards the topic Optical Instrumentation for Industries. I must mention my deep sense of appreciation to Dr. Manoj C for his explanation of applications of ultrafast spectroscopy for the study of biological systems. I'd like to express my sincere gratitude to Mr. Venkatakrishna Bharadwaj for giving an excellent coverage to his topic, Spintronics, exploiting the dual personalities of electrons to new possibilities for information storage. We are all inspired by your great words. I would like to take this opportunity to express our gratitude to our beloved principal, Reverend Father Dr. Babu Paul CMI, who guided and supported us to conduct this successful event. Now, I would like to thank Reverend Father Anthony CMI, who supported us with his valuable advices and suggestions. Well, an event like this cannot happen overnight. The wheels started rolling months ago. It requires planning and a bird eye for details. I have been fortunate enough to be backed up by a team of very motivated and dedicated colleagues of Department of Science, headed by Dr. Sangeeta George. I would like to thank Dr. Benjamin, Ms. Shilu Varghese from Department of Management Studies, who helped in framing the international webinar. I would like to thank Mr. Azul, who took care of the technical side, which helped in the smooth conduction of this event. I would like to thank our students, Ms. Anna, Ms. Varmita, and Ms. Rohini for the support they have rendered. Last but not the least, I would like to thank the representatives from various colleges and universities for participating in this webinar. It's been a great pleasure. Looking forward to meet you again. Thank you.
Thank you, ma'am. Feedback form is shared in the chat box, requesting all the participants to fill the same. And once again, thank you all.